decided that he wanted to be a physicist, and then once he figured out that you could be a physical chemist, which takes physics of chemistry, push them together, you were sold at that moment, I think.
Absolutely.
Anyway, so we've been working together. All the while, Wes has been in my lab. He's also been in the football team and the track team, and there's another team, like a just intramural soccer team, and what else?
Every now and then.
Every now and then. My goodness. Work ethic extraordinaire, which is fantastic because when he ventures off into University of Wyoming to continue to get a PhD in physical chemistry. So exciting. Anyway, well, I'm so excited to have him share the materials that he presented at the National American Chemical Society meeting in San Francisco just 7 weeks ago. So, without further ado, Wes Hetcher.
Thank you, Dr. Fleshman. Really appreciate that introduction. Speaking first off, I will be talking about ionic liquids and their transport properties. If you read this title, it's how a modified transition state theory explains counterintuitive trends in ionic liquid transport properties. So we have a few terms we need to define, but first I'll start off with what exactly we're looking at and why we started looking at it in the first place. So when I first joined Dr. Fleshman's research group, she presented me with this paper by Patricia Hunt entitled, "Why does a reduction in hydrogen bonding lead to an increase in viscosity for the 1-butyl-2,3-dimethyl-imidazolium-based ionic liquids?" And this title is a question, which is kind of weird for a lot of scientific papers. That's not quite common. In this paper, Patricia Hunt explores the main problem of higher interactions within a liquid corresponding to decreased interactive properties. So these liquids are interacting more strongly, but showing properties that correspond to fewer interactions. This approach was computational, so she and her group were doing all of this in such programs like Gaussian that some of you may have seen in your own individual chemistry labs. And they were looking primarily at ionic liquids. So what exactly are ionic liquids? They're just salts that are made up of ions. If you think about regular salts, such as sodium chloride, you've got a small sodium atom corresponding with a smaller chloride ion. And these are charged ions with a positively charged cation and negatively charged anion interacting strongly. If you heat up table salt, you spread out those charges because of thermal expansion of the liquids, and that spreads the charge out, creating a liquid instead of a solid around room temperature. You could do this same sort of process by just increasing the size of the ions, so you can have a larger cation and larger anion be a liquid around room temperature. We define room temperature to be below about 100 degrees Celsius. The nice thing about these ionic liquids, besides being liquid around room temperature and easy to work with, is that they're tunable. So you can define the specific structure of a cation or anion to be whatever ideal structure you propose, and then it will have different transport and other chemical properties depending upon the exact structure. Most ionic liquids have low vapor pressures. Because they're liquid around room temperature, it takes a lot of energy to get them into the vapor phase and evaporate them off of any sort of system that you're working with. They also have a large electrochemical window, so that means that the ionic liquids are able to conduct charges throughout the system effectively and among a wide range of frequencies. All of these things make them very preferable for use as green solvents, so you can perform a reaction in these liquids and then evaporate off your reactant and products and be left with whatever you were reacting it within, these ionic liquid solvents, for reuse again and again, and for ensuring that you're evaporating off only what you're looking to retain. They're also being used in engineering as lubricants, and particularly in batteries. These large electrochemical windows make them preferable for use with lithium-ion batteries and advancing the future of chemical storage of electricity. They're also finding a place in cosmetics. So because of the low vapor pressure, they're not spending a lot of time in the vapor phase, so they can hold on to some fragrance or perfume and then release them when agitated. So the specific liquids that the Hunt group was looking at are these 1-butyl-2,3-dimethyl-imidazolium-based ionic liquids. And this just means that the imidazolium cations have various alkyl chain lengths, and we're looking primarily at the comparison between this cation and that cation. If you don't really need a lot of chemistry background to notice that there's a stick right there. So this just means that at the C2 position of this 5-membered ring, there's an additional methyl group, which is important for the hydrogen bonding that can occur, which we'll get to in just a little bit. So this 5-membered ring containing 2 nitrogens is the imidazolium functional group that is the basis for a lot of these ionic liquids that we're going to be looking at today. The Hunt group used a constant anion of chloride so that for their purposes they were doing a computational approach, and it's just easier to computationally model small individual atoms instead of looking at larger, more complex structures. So that's the system that the Hunt group was looking at, and they were exploring viscosity. Now, we're going to investigate viscosity as more of a generalized transport property. So a transport property is just moving throughout the liquid. So we see a lot of different examples of what transport can mean. We have diffusion, which is the transport of mass throughout a liquid, the viscosity, which can be the transport of momentum, or the conductivity, which is transferring a charge. Now, transferring a charge in ionic liquids is primarily important because the ions themselves have a positive or negative charge. Important in the understanding of viscosity is that these all exhibit some functional dependence with temperature. So we see that the diffusion, conductivity, and viscosity, which is also the inverse of fluidity, perform similarly with an increased inverse temperature when you take the natural log of the transport property. So we see this consistent curve for each of the transport properties. And in the case of viscosity, we can relate this to a very similar example of honey being very viscous. When you heat up honey, it becomes less viscous or more fluid. So we see that the natural log of the fluidity for an increased temperature, which would be a decreased inverse temperature, a decreased inverse temperature corresponds to an increased fluidity. These curves, because they're not straight lines, require a lot of empirical fitting parameters, the most popular of which is this Vogel-Tauman-Fulcher equation. So that in the case of diffusion, we model the diffusion as this exponential prefactor d0 times the exponent of the b term over t minus t0. Now this is an empirical parameter, this is an empirical fit, so although you can use it to predict a lot of the points along the curve, it doesn't give any sort of indication of the actual molecular model of transport and how these liquids interact as they're moving around. So we have now a necessity for the definition of hydrogen bonding. Hydrogen bonding is simply some form of dipole-dipole interaction. We know that there is a donor and acceptor atom within these systems. The donors typically are nitrogen, oxygen, and fluorine, which are strongly electronegative atoms. And although this is a contentious point, carbon is actually able to donate hydrogen into a hydrogen bond when it's bonded to an electronegative atom. Acceptor atoms include nitrogen, oxygen, and fluorine because they have a lot of, they typically possess excess electrons with which they can accept this bond between the hydrogen and its own atom. So we see that the bond between the hydrogen and acceptor atom is typically a little bit longer than the donating bond between the donor atom and the hydrogen, about generally 2 to 3 angstroms, whereas the donating bond is a lot shorter. So we see some examples of hydrogen bonding. In this case, we have water, which is just H2O. It is an intermolecular homogeneous hydrogen bond because the donating oxygen is identical to the accepting oxygen. And this is intermolecular because it's not the same molecule doing the donating and the accepting. So we see that each of these hydrogens can correspond to any one of the surrounding oxygens. And on average, each oxygen within a water-based system can accept about 6 hydrogens in hydrogen bonding. Other examples of hydrogen bonding include intramolecular, so within the same molecule rather, we have one hydrogen bond, and this is an example of a heterogeneous hydrogen bond because the donating nitrogen is not identical to the accepting oxygen. We can see this in ionic liquids, so for some arbitrary large anion with accepting atoms, there can be intermolecular hydrogen bonding. This is the previously mentioned CN-Min cation, or imidazolium-based cation, with the hydrogen at the C2 position being donated into this arbitrary large anion. Now, if you recall, the hydrogen bonds typically interact intermolecularly and are strong-ish dipole-dipole interactions. So we know that for increased hydrogen bonding, there should be increased interaction between the molecules, which will correspond to a more difficult process of moving throughout the liquid. So we should see, since viscosity is a measure of how resistive a liquid is to flow, that increased hydrogen bonding corresponds to increased viscosity, but the inverse is observed, and that's a very counterintuitive point, which we're going to try and explore. Other groups have done a similar thing, have approached this same problem as the Hunt group. The Fomino group, I believe they were from Germany, explored the exact nature of hydrogen bonding in the far infrared region, which corresponds to the number of hydrogen bonds that can be explored. They used the same CN-Min and CN-D-Min ionic liquids. This paper is by the NOAC group, and it explores exactly the role of the C2 position in these ionic liquids and how these ionic liquids interact. So the NOAC group performed spectroscopy, both IR and NMR, to explore why these hydrogen bonds impact the liquids the way they do. These were both experimental approaches, so the groups actually had the liquids in their possession, whereas the Hunt group did it entirely computationally. So this is, once again, Hunt's title, Why a Reduction in Hydrogen Bonding Does What It Does for Ionic Liquids. And if you recall my title, How a Modified Transition State Theory Explains Counterintuitive Trends in Ionic Liquids Transport Properties, we have some overlap between the terms. We know that there's ionic liquids being investigated, the transport properties is how we're defining them, and there are counterintuitive trends for these transport properties. In the Hunt paper, this counterintuitive nature comes in the form of a question. But what exactly is a modified transition state theory? That's the question we're going to answer right now, so that we can understand how this approach answers Hunt's question. So a transition state theory in general is how a reaction typically goes from point A to point B. So how we get from reactants to products. For a generalized reaction, the p-chemist's favorite reaction, going from A to B, we have a rate constant defined by this Arrhenius equation. K, the rate constant, is equal to this exponential prefactor C times this Boltzmann term, the exponent of the negative EA over RT. And we'll get to what the EA is in just a bit. The temperature, the T being the temperature, R being the gas constant. We can linearize this form by taking the natural log of both sides of this equation and get this more linear form of the rate constant Arrhenius equation. And we see that doing so, we can plot the natural log of the rate constant as a function of inverse temperature and get this straight line. From this straight line, we can see that the slope is related to the activation energy, this EA term. Now this activation energy is how much energy the system must have to reach this transition state, or this activated complex state, in order to proceed from reactants to products. This is generally referred to as a barrier, some sort of a push that the molecules need in order to go from their standard state into a more transitional state. Similarly to reactions in general, we can look at transport of molecules. So if we have a target molecule in red here, it requires some amount of energy to break the interactions of the surrounding molecules and get into this activated transition state where it's not interacting with any of the surrounding molecules and has some space to move so that it can go from this activated, more higher energy state to a more relaxed, newer position within the liquid. So we call this a modified transition state theory because if you recall, on here we have a temperature dependence in the Boltzmann term times an exponential prefactor that's generally referred to as a constant. So we can't identify these activation energies if these log against inverse temperature plots are curved. Now if you recall, for most of the transport properties we were looking at in liquids, these are strongly curved, which requires these empirical parameters. What we do is we apply the CAF, which is the compensated Arrhenius formalism, to linearize this curved line. This compensates for the curvature through a scaling procedure, which we'll get to in a little bit, to explain how this curvature becomes straight. So when we apply the CAF, we get a straight line from this natural log of fluidity over reference fluidity. Again, I'll get to that in just a little bit. And from this straight line, we can now determine activation energies. These activation energies are defined for specific functional groups. So if you recall, the imidazolium-based ionic liquids we're looking at have that specific five-membered ring structure, and that family is what determines the activation energies. So the reason we're trying to apply the CAF is to find activation energies of these ionic liquids, and the activation energy is dependent entirely upon the structure of the functional group or the structure of the family. So we have all that we need to find is in the family. It's all in the family. That's my It's a great joke.
It's a good.
All right, so we apply the CAF and we get these compensated fluidities or reference fluidities to identify activation energies. Now we're going to look at these specific cations and comparing the same two cations that the Hunt group did. Or rather, we're going to compare the same two functional groups that the Hunt group did. We're going to use the same anion, however, that the NOAC and Femino groups were looking at. This bis-trifluoromethylsulfonylamide anion. That's a mouthful, so we just call it TFSI. So the question, if you recall, we have this stick at the C2 position, so why does reduction of hydrogen bonding increase viscosity can be rephrased as why does a methyl group at the C2 position increase viscosity? So we've rephrased our question as to define why we have a different functional group and why that has a different activation energy. So we've observed, it has been observed by both us and other groups, the NOAC, Hunt, and Femino groups, that there is additional hydrogen bonding in the CN-MIM cation and lower viscosities, whereas the CN-D-MIM cation has weaker hydrogen bonding and increased viscosities. We know that there's weaker hydrogen bonding because only 2 of the carbons can donate hydrogens into a hydrogen bond, whereas in the CN-MIM cation, 3 hydrogens can be donated, creating stronger interaction. So we expect, because there are increased interactions in the CN-D-MIM ionic liquid, the one on the right, that there should be a higher activation energy determined from the compensated Arrhenius formalism. That is, methylation at the C2 position increases the barrier that is required for transport to occur. So if we observe the fluidity of some system, specifically our system, in the C6 methylimidazolium TFSI, we can describe the log of fluidity against the inverse temperature through this, again, Arrhenius equation. The natural log versus inverse temperature plot is shown here. The R squared is about 0.995. That's a very straight line for any biologist, but it's not great for a P chemist. If you look very closely, you can see at the higher end, so the higher the temperature, we start seeing larger deviations from this curve, and at the lower end we see increased deviations from the curve. So it's actually quite curved, but it's not quite visible on this scale. So we know that the only temperature dependence of this Arrhenius equation is within the Boltzmann term. Or when we linearize this to get the R² value, the only temperature dependence is in this slope. The F0 prefactor, the fluidity prefactor, has no temperature dependence itself. If we compensate for the fluidity through this scaling procedure that we'll get to in just a minute, we find that the R² value is 0.9989, which is fairly good for just about anybody that's looking to do some sort of linearization, maybe not a physicist. So we see that the natural log, the plot of natural log of the fluidity over the reference fluidity has a more straight line and is actually higher in this scale than just the natural log of the fluidity. We can, in this case, identify the activation energy from both the slope and the intercept because of how we've defined the functional group, or how we've defined the prefactor and the rest of this compensated Arrhenius equation. So we're able to identify two different activation energies which actually end up being the same or roughly the same because they're dependent entirely upon the functional group at the head of the cation we're exploring. So what we want to do is actually look at these ionic liquids. Unlike Hunt, we don't have very strong computing power, so we're going to do it ourselves with the liquids we have. Previous research in the Fleischmann group has looked at these CN- TFSI ionic liquids. So we had a bunch of that on hand, but we didn't have any CN- TFSI. So what we had to do is we had to decide how we would obtain these ionic liquids. We could purchase them ourselves, but to get 4 of these and 4 alkyl chains in order to find the functional group, we would need to pay upwards of $3,000 for a tiny little vial of very expensive liquid. So that isn't extraordinarily cost effective, and we wouldn't have any excess if somebody were to break a bottle, as people have been known to do. But what we could also do is synthesize them ourselves. In the literature, we've seen that these ionic liquids have been synthesized as early as 1996, and it's a fairly straightforward process, and as you can see, fairly inexpensive compared to purchasing the individual liquids themselves. So we can do it for about 1/5 of the cost and recreate this synthesis whenever we need excess ionic liquids. So that's what we did. We synthesized these ionic liquids in 2 steps. The first step was taking this 1,2-dimethylimidazole, which is a 5-membered ring without an excess alkyl chain on it, and reacting it with a bromoalkane of 4, 6, 8, or 10 carbons in length. This was done in toluene under a nitrogen atmosphere at 80 degrees Celsius for about 18 hours. So this is just a straightforward SN2 substitution reaction where the bromide attacks the excess electrons on the N1 position of the imidazole, excuse me. We performed this in 1-to-1 molar equivalents so that we could retain as much of the ionic liquid as we could, and this was again done under a nitrogen atmosphere. These ionic liquids, similar ionic liquids rather, have been known to be very hydrophilic, so they absorb a lot of water, and so we wanted to avoid any sort of contamination during this step of the synthesis. And we are left with this 1-alkyl 2,3-dimethylimidazolinum bromide ionic liquid. This is a bromide anion, which is similar to the Hunt's approach of using a chloride anion, but we're looking, because we have CN- TFSI, to replace the bromide with a TFSI anion itself. So the second step of our synthesis is to take what we've already created and mix it with lithium TFSI. This lithium TFSI performs an anion switching step where the TFSI replaces the bromide in the ionic liquid due to its large size and thermal stability. This was then placed, the resultant ionic liquid was then placed in a vacuum oven for about 24 hours. If you recall, these ionic liquids have an extraordinarily low vapor pressure, so placing them in a vacuum oven, we can evaporate off all of the excess liquids that might have been obtained throughout this process, and we're left with a relatively pure ionic liquid. We observed a yield of about 65 to 83% for the 4 ionic liquids we were looking for, which is, I think, pretty great for a physical chemist doing organic chemistry for the first time. We then wanted to confirm that we had what we thought. So these ionic liquids were, we performed an NMR, nuclear magnetic resonance spectroscopy on these ionic liquids from the 4 to 10 carbon chain length. This verification was compared via the hydrogen environments to the NOAC group's syntheses. We see for these peaks, it's not the point of this talk to go through each of the peak identities and how they correspond to the ionic liquid themselves, but we saw for our NMR that it corresponded very strongly to the NMR of the NOAC group. So we feel very, very confident that we have what we were intending. And this is just a picture of the 4 ionic liquids that we were able to synthesize this summer. We then confirmed that we had the types of interactions that we wanted via IR. Now IR is infrared spectroscopy, and that was performed so that we could notice the exact functional groups that are interacting in these ionic liquids. So because NOAC had done this exact synthesis, we were able to compare specifically to their group and notice identical features. Specifically, we see in this region, the 2700 to 2900 wave number range, that we have about three peaks that are consistent throughout all 4 of these spectra. The top 2 spectra are the NOAC groups, and the bottom 2 are what we were looking for, or what we had synthesized. The first and third spectra correspond to CN-D-min TFSI, while the second and fourth correspond to CN-min TFSI, the cation of which is shown here. So this 2700 to 2900 wave number range corresponds to the carbon-carbon stretching modes of the ionic of the structure. So we see that that region of the spectra corresponds to this alkyl chain length of the cation. Excuse me. And we know that because the alkyl chain length is identical and the functional group is what's changing, the alkyl chain length interactions in the IR should be identical for the CN-min and CN-D-min, which is shown in this correspondence. Then we see that the hydrogen bonding range, so about 3000 to 3200 wave number, that there are 3 peaks in the CN-min TFSI, which correspond to the 3 different hydrogen bonds that can be donated by the CN-min cation. Comparing this to the CN-D-min cation, we see only 2 peaks in both our spectra and the NOAC spectra, which indicates that we have different hydrogen bonding between the CN-min and CN-D-min, and that it corresponds very strongly to what the NOAC group had seen. So next, we collect our data. We get all of the viscosity data that we were looking for. We're going in the temperature range of about 5 to 85 degrees Celsius. We have 2 families of 4 ionic liquids each, and we want to collect viscosity and density data. Now, viscosity and density data are required because we're going to convert them to fluidity and dipole density. Now, fluidity, as previously explained, is just the inverse of viscosity, and dipole density is related to the density because the dipole density is the number of dipoles observed in a unit volume. This is related to the density because we know the exact structure of the ionic liquid in question, and so we know approximately how many dipoles there are per molecule, and then how many dipoles there are in some unit volume when we know how many molecules there are in some volume. So we collect the data of viscosity and density, convert it to dipole density and fluidity, and plot it here, with fluidity on the y-axis and dipole density on the x. This shows 4 curves corresponding to 4 unique ionic liquids ranging from 4, 6, 8, and 10 carbon chains in length. And we see that for increasing carbon chain length, there is a decrease in the corresponding dipole density. This makes sense because as the groupings get larger, we can fit only so many dipoles into a specific volume. We also see that the increase in temperature corresponds to a decrease in dipole density because as the temperature increases, there's a thermal expansion of these ionic liquids. So we see that for each of these ionic liquids that there is an increased dipole density for increased temperature. Now we select a single one of these ionic liquids. In this case, we're going to look at C8-TFSI, and we need to select a reference temperature by which to compare it. So each of these curves, as you can see, correspond to a specific temperature, and so they are isothermal. We select one of these isothermal curves, which has a similar region of dipole densities as the ionic liquid we're looking at. So for the case of C8-TFSI, we're going to look at the 55-degree temperature curve. This shows good correspondence between the dipole density range of the temperature curve and the ionic liquid we're trying to define an activation energy for. So using this isothermal curve, we create a reference temperature curve, a reference curve, which is defined as a second-order polynomial so that we can then project the ionic liquids onto this same curve. If you notice, all of these lines are exactly straight up and down, so that the dipole density of the fluidity value we have is identical to the dipole density of the reference curve value we're looking for. So this functional form has been defined, and we project the ionic liquid onto this reference curve. This creates reference fluidities for the ionic liquid in question, which is this F of R as a function of T of R, which we saw a little bit earlier. So then what we do is we take our fluidity and divide it by the reference fluidity. This is a pretty simple procedure, and this cancels off the prefactor in the compensated Arrhenius formula, in this equation of the compensated Arrhenius formalism. So because we're using identical dipole densities in the fluidity and the reference fluidity, we can cancel this off, and we're left with just this simplified or semi-simplified form of a compensated Arrhenius equation. We take the natural logarithm of this more complex equation so that we can linearize similarly to how the transition state theory linearizes the rate constant of some reaction. And we're left with this natural log of the fluidity over reference fluidity equal to this activation energy times the inverse temperature plus some activation energy over a reference temperature term. So if you notice, we have activation energy showing up twice in this equation. This is repeated for each of the family members, so we get 2 activation energies per family member, so we get 8 activation energies per family. These are then averaged, and we look for a specific family to define these activation energies. If you recall, the ionic liquid we're looking at in this case is the CN-TFSI, and we had seen that there's more hydrogen bonding and lower viscosities, and we see that there's an activation energy of about 37.5 kilojoules per mole. Then when we look to the CN-TFSI, which had weaker hydrogen bonding but larger viscosities, there's an activation energy of about 42 kilojoules per mole. So we see that the activation energies are different for different functional groups, and this is exactly what we were looking for. So if you recall, we had tried to find an activation energy for each of these families to indicate why to indicate that there is a higher barrier with which one of these liquids must attain in order to transport throughout itself. So the question is, if the original question was, why does a reduction in hydrogen bonding lead to an increase in viscosity? We haven't answered this question with the activation energies. Within the past year, Allison and a former Lawrence student, Grant Forsyth, published a paper shown here relating the CAF to 3 and 1 alcohols, and they explored how hydrogen bonding occurs how hydrogen bonding shows up in the CAF. So we know that there is some hydrogen bonding going on in our ionic liquids, but it's not anywhere to be seen in the activation energies. It must be within the prefactor. And this is our basis for why we can look at the prefactor to observe these hydrogen bonding effects. So we need to isolate the prefactor in order to find where this hydrogen bonding lies. If we take the compensated Arrhenius equation and just do a simple little bit of algebra, we get the prefactor as a function of the fluidity over this Boltzmann term. If we look for the exact nature of the prefactor, we find that from first principles it's been derived by the Petrowski and Freck group, from which Allison comes from the University of Oklahoma. They've derived an exact structure of the exponential prefactor for diffusion. Now, we've done all of this work with fluidity, but not diffusion yet, so we don't have any idea what the form of the prefactor takes for fluidity. So if we want to look at the nature of the prefactor and where hydrogen bonding occurs, we need some diffusion data. So that's the next step, is to take the diffusion data as well as conductivity to identify what the activation energies are and whether there are any, whether the prefactors can tell us anything about the nature of hydrogen bonding. Looking more closely at the prefactors, we get from this original data, which you've already seen, the fluidity values can be converted to these fluidity prefactors, which follow this very nice curve. We do this for CN-min or CN-dmin rather, and CN-min, and see that the fluidity prefactors are similar. However, if we look at the prefactors compared between these ionic liquids, they're nothing, well, they're pretty similar, but they're not quite alike. We see that for the entire range of dipole densities explored, that the CN-dmin TFSI has a larger exponential prefactor. And this will be explored more closely in the coming weeks when we look at the exact nature of the prefactor once we have diffusion and conductivity data. So to conclude, we have two activation energies, and they're different for the functional groups. So the functional groups we've looked at have different activation energies, and so we can say that they're not the same, and there's some relation to hydrogen bonding as to why the fluidity prefactors of CN-dmin are higher than that of CN-min. An analysis of these prefactors requires conductivity and diffusion data, however, so we can't yet say anything about the nature of why these prefactors are higher for one than the other. That means the next step is to take conductivity data of these ionic liquids with this nifty little instrument here. And additionally, we need to, again, verify that these ionic liquids are what we think they are, so we're going to look at water contamination via Carl Fisher titration once we get an instrument that actually works. I'd like to acknowledge Stefan Debert for all of his help with the organic syntheses that I was doing this summer, as well as Daniel Martin and the Lawrence University stockroom for the glassware, and occasionally a little joke or a piece of bread when I was hungry. I'd also like to thank the Senior Experience Funding through Lawrence University that, as Allison mentioned, was able to send me to San Francisco to present this at the National ACS meeting. It was a wonderful experience, and I can't be grateful enough for that opportunity and the people I met and the experiences I had going out west. I'd also like to thank Allison for all of her help. She's not on the slide because she's just too too important and whatnot. So she deserves all the accolades for working me through the CAF again and again and answering all the questions I had. I still have more for her, I'm sure. I'd also like to thank Chris Van Heusen for his work this summer. We were doing a similar project, and he gives his talk on Monday, so stop by if you want a refresher of the CAF. I'll be sure to be here so that I can understand it a little bit better too. Any questions? Chris?
When we originally talked about the CAF being a modified transition state theory, and we think about the energy of activation, when we think about the energy of activation going from being the reactants to a transition state down to products, do we think of the energy needed to break those intermolecular interactions, right? That's what we're thinking of that as. Wouldn't that encompass hydrogen bonding within the EA that we would see?
It should. There should be some amount of energy needed to break those dipole-dipole interactions that are hydrogen bonding. And that probably does factor in a little bit to the actual value of the activation energy, but we don't know specifically how much that would contribute. And because we don't know where the activation energy comes from in either of the structures, we can't say definitively or even speculatively what amount of the activation energy comes from breaking hydrogen bonds. Any other short answers? Chris?
No.
Or Deanna?
Let's go.
No, you're right first.
I did that.
So I just, to help me wrap my head around this, is this going to be an activation energy for diffusion, an activation energy for fluidity, or is it the same activation energy throughout that's just about movement?
There should be a unique activation energy for each transport property. There is a difference because they correspond to different motion through the liquid, that is, diffusion is mass transport and conductivity is charge transport. There's a different sort of energy barrier that's required to break the interactions to move a charge than there is to break the interactions to move a mass. So there should be slightly different activation energies, and we actually explored the fluidity, the fluidity activation energy first, because it should be the lowest, and we should see increasing activation energies through conductivity and diffusion. Anyone else? Chris?
Okay. Do we know that at the C2 position we're actually having hydrogen bonding occurring? Has that been already verified, or
Yes.
is that okay?
Yes. That was verified by the Fonino group, and we also see it in the absence of a peak in our own IR spectrum.
Okay.
Allison?
So if you were here for another year, where would you take this project next?
The next step in this project, I would say, is likely to be collecting the conductivity and diffusion data, obtaining activation energies, looking at what the prefactor exactly says, and then writing it all up and sending it to Jax.
To Jax? Really?
I don't know.
That'd be cool.
Yeah, so the CAF. Any other questions? Yeah.
So of course I'm going to ask the contamination question.
Yeah.
So you said you got really high purity because it could all outgas, but then later on you mentioned that you were a little worried about water contamination. Can you reconcile those two statements, and can you talk a little bit about how you checked that you got really high purity? What exactly are you looking at to say that?
We need to, we should probably perform some HPLC just to know that it breaks up the way we think it does. That's something we thought about but didn't have the time to explore. And it could could indicate some purity issues. But we're looking specifically at water because a lot of similar ionic liquids are hydrophilic. And just that is one of the staples of the procedures in order to publish work with these ionic liquids is to make sure that there's water. Because there are papers that have shown that water is a strong contaminant in these sorts of ionic liquids.
Did you find a study that the HPLC was using these liquids?
They're-
And do you know what kind of, I mean, I'd be worried about like throwing it on our HPLC.
Oh yeah,
Okay.
it would be a very, very different column than we have, that's for sure. There was definitely one that looked at purity through HPLC though.
Is
At
it
least
an ion column or anything? Sorry, you might not remember. I'm
I
sorry.
don't
Pat,
know.
you just piqued my interest.
So the,
Didn't
so the
do that.
viscosity may or may not even be a function of the activation energy at all. Is it, or is there any connection?
The viscosity is the inverse of fluidity. And
Right.
so if we can make the claim that the fluidity is a function of the, if the fluidity is described via this modified Arrhenius equation, then we can also say that the inverse of viscosity, or the inverse of viscosity is defined via this compensated Arrhenius formalism. So it's not, I don't believe that we can directly use a similar scaling procedure, but we can convert them, by converting them to fluidities, we're looking specifically at the transfer of momentum through these liquids. So fluidity is more precisely how the liquid flows, and it's, the viscosity is the resistance to some flow. And if we just comparing the two, we can describe at least one of them via CAM. Any other questions? Thank you very much.